Hello, my name is Yan Liu, and in this video, I will review the third and final academic paper for course COMPX529. This paper talks about auto-adjusting self-adaptive software systems. The authors are Zoltan Anderman and Andreas Metzger, and this paper was published on the proceedings of the 15th IEEE International Conference on Autonomic Computing on September 2018. Self-adaptation has been designed to cope with dynamic environments. However, in some situations, adaptations are done in a way that is not fit for the purpose. For example, some adaptation actions may take more time than others, or if the environment is not monitored with appropriate frequency, significant changes can happen in a time period that is smaller than the sensor monitor frequency. Then the adaptation logic may not be able to timely observe and handle these changes. This paper shows a real workload of a cloud service. In different periods of time, the workload exhibits different dynamics. In such highly dynamic environment, it's not sufficient to only adapt the system. The adaptation logic itself must be dynamically modified to address the changing adaptation requirements. So dynamic adaptation is required as a systematic way to detect the current dynamics and reason on how the adaptation logic should be operated to cope with it. Why is it still a problem? Well, it is not easy to design the adaptation logic in such a way that it can effectively cope with different kinds of dynamics. And the existing approaches to self-adaptation do not solve this problem. For example, running the adaptation logic with the highest possible speed and frequency prohibits computationally expensive optimizations, even if such optimizations would be sometimes possible. Running the hierarchical approaches, such as three-layer architecture, change the adaptation logic only after observing that the adaptation logic is not appropriate in the current context, which may be too late. Online learning approves the adaptation logic by a trial and error process, which may require many observations to converge, with negative consequences on the live systems. To address this problem, several authors suggested adding extra layers to a self-adaptive system's adaptation logic. The first such approach was the three-layer architecture, in which the managed element is adapted using reactive plans by the adaptation logic of the middle layer. Other hierarchical approaches use online learning to improve the performance of the adaptation logic. Several authors proposed adopting methods from control theory to engineer self-adaptive software because of the similarities between the two fields. Particularly relevant classes of systems in control theory are auto-turning system and adaptive control, which are capable of optimizing their own parameters to optimize the fulfillment of an objective function. However, auto-turning for self-adaptation software systems is challenging and has not yet been successfully achieved. To tackle this issue, the authors introduced an approach called auto-adjustment to keep the adaptation in line with the changing dynamics. They use the well-known MIP model as a basis, as shown in this picture. This first picture, their approach adds a further step called auto-adjust. The auto-adjust step continuously accesses the situation using the data provided by the monitoring step and automatically configures the MIP steps so that their behavior is always aligned with the current situation. So how does this newly added layer work? Well, this picture shows the interplay, the logical connections between the MIP steps and the auto-adjust step. As a whole, auto-adjust layer gets information from monitoring and may set parameters of each MIP step or the MIP loop. The input of auto-adjust is retrieved from the output of monitoring that also used by the analyze step. This way, no further sensors are needed for auto-adjust. The existing sensors can be reused. The outputs of auto-adjust control the way the adaptation logic works. The operation of the adaptation logic should be controllable through a set of parameters, and that's why it requires the MIP steps to configure their adaptation logic with appropriate parameters. The processing logic is shown as the second picture. Let the input of auto-adjust be a vector X of monitoring data from some domain D. The output of auto-adjust is a vector Y of parameter values in the range R. For example, the auto-adjust identify servers that are likely to become overloaded soon, quickly find a plan for test allocation, and determine appropriate parameter settings based on the situation. How is this better? Well, the hierarchical approaches that mentioned in related works are based on two critical assumptions. First, it is assumed that the environment is largely stable, so in highly dynamic environments, those approaches are not appropriate. They may lead to non-acceptable delays. The second assumption is that suboptimal adaptations can be tolerated. This implicit assumption may not hold in some domains because a bad adaptation can lead to wide-range negative consequences. But with this approach, it avoids both assumptions and can timely recognizes the need for changing the adaptation logic quickly reconfigures it appropriately. Therefore, it is better suited for highly dynamic environments. So the authors evaluate their work by implementing it on Cloud Sim, a widely used cloud simulator. In the experiments, they simulated a cluster of 100 servers hosting 500 VMs. They performed 3 different approaches, and the summarized result is listed in the picture. The first one is a built-in consolidation algorithm, which is a fast heuristic. The second one is ILP, which is an algorithm using integer linear programming. Then the third approach is auto-adjust. Auto-adjustment activated the emergency mode when the load was quickly rising, while it remained in normal mode in all other cases. From the result we can see concerning server overloads, the auto-adjust approach achieves the best result. This shows that auto-adjustment can lead to a substantial benefit. Well, here comes the critique. Firstly, the work is based on an assumption that reconfiguring the adaptation logic by changing parameter is fast. However, adding this extra step requires not only the processing time of the auto-adjustment itself, but also the interaction time between it and every step of MIP. The complexity of network may also add uncertainties. The impact of this area didn't show in the paper. Secondly, this solution requires all MIP steps to configure their adaptation logic with the appropriate parameters. That add extra requirement for other MIP steps. Thirdly, the work was implemented on Cloud Sim. However, in a real cloud environment, there are differences in many areas could impact the effectiveness of this solution. The differences are also worth to be pointed out to provide more solid support for this model.